Hi, in this video, we should continue studying more examples of groups, and one of the important ones is known as a symmetric group. So a symmetric group is just defined with the set of all bijections from omega to itself. And under function composition, this set forms a group. And this is because the composition of two bijective functions is still bijective. So you can think of them as a permutation of the elements inside omega. And the identity would then be just the identity function. And so that's why it's sometimes noted as the permutations of omega. When omega is finite, then it's given a symbol known as Sn, with the order being n factorial. And really that's because, like in counting cases, the number of permutations for n elements is n factorial. And so it's the same counting argument as you done in other classes. And we denote this permutation using a disjoint cycle notation. And this disjoint cycle notation really can be written as the following. For example, you have a function sigma that sends 1 to 3, 2 to 2, 3 to 5, 4 to 1, and 5 to 4. What you're saying is 1 is sent to 3, and you can go 3 to 5, 5 to 4, and 4 back to 1. And you can see 2 is trapped within its own cycle. And so we can write it in terms of these two cycles over here. So it's, you have 1 4 cycle and 1 cycle. And this really just means 3 goes to 1, 1 goes to 3 I mean, 3 goes to 5, and 5 goes to 4, and 4 goes back to 1. And so you can see the picture over here, and the product of all these cycles is known as the cycle decomposition of sigma. Now, this cycle decomposition is unique up to the permutations of the cycle within them. So you can just write A2 goes to A1, A2 goes to A3, all the way to AM1, and then the last number now is A1. So you can bring this all the way to the back, or you can bring this 2 all the way back. But as long as you keep the order within it in the same descending chain, then they are the same cycle. And also those length ones, they can be removed as they don't really play an important part when you do composition of them. And you see over here. So we can see that the sigma representing n equals to 13 can be represented in the following form. And the length of each cycle is known as a T cycle. So this is 1, 2, 3, 4, 5. So this is known as 5 cycle, 2 cycle, 1 cycle, 3 cycle, and 2 cycle. So it is the product of 5 disjoint cycles, because none of the elements are repeated, of the following cycles of the following length. And we usually adopt that 1 cycles unwritten, because they don't really affect the notation much. And if they are not written, it just means that the number is within its own cycle. So you can just write as this and remove the 3, and this just, we take it in convention that 3 is its own cycle. And when you compute the composition of two functions now, this cycle notation can help you. As 1, 2, 3 composed with 1, 2, 3, 4, then you know that the number 1 is sent to 2, so by the first, then the second permutation sends 2 to 3. So you can just, it'll be ending with, it'll end with 1, 3, and then now you ask where 3 is sent to. Well, 3 is sent to 4, and in this case, 4 is trapped within itself, so it's 1, 3, 4. And then the next one is from 4 you go to 3, and from 3 you go to 1, so it's 1, 3, 4, and you're back to 1, so you're done with this cycle. And then you ask yourself, 2 is sent to where? So 2 is sent to 1, and 1 is sent to 2, so 2 is trapped within itself, so you don't need to include it. And next you can show that an L cycle has order L, and it should be quite straightforward, and I'll outline the sketch. So you can just think of it as a cyclic group generated by sigma. And that's because the cycle is of the form A, and the next one is actually you apply the sigma to A, and the sigma to A, sigma squared to A, and so on. And so you can just think of them as after the length L, the last integer, it goes back. So you can just write it as a cyclic group generated by an element A. Hence, an L cycle has order L. And so now we can define what is known as an inversion. And an inversion is just defined as the ordered pair, where when I is less than j, but sigma I is larger than sigma j. And we just denote the set of all inversions as x sigma. So pictorially, it just means that, let's just say 1 is sent to 2, 2 is sent to 3, 3 is sent to 2, and 4 is sent to 5, and 5 is sent to 4. Then we know that these points where they cross, we can call them the inversions. Because now 2 is sent to 3 and 3 is sent to 2. So it fulfills this condition. Since 2 and 3, sigma 2 is 3 and is larger than 2. And so these are the inversions. So it's just 2, 3 and 4, 5. So it corresponds to where these maps intersect each other. And if the elements in this x sigma is odd, the number of elements is odd, then we say that sigma is an odd permutation. And a similar definition for even permutation, where the number of elements in x sigma is even. And now we come to the lemma that we want, and it says that the number of elements in sigma tau is congruent to the number of elements in sigma plus the number of elements in tau mod 2. And I'll just give you a sketch of the proof, and you can write out the details for yourself. But really, once you understand this picture, you understand the proof. So you just need to split into cases. And in the first case, of course, you could have an inversion for tau, but not sigma. So it crosses over here, but there's no crossing here. And this means that you add one crossing for sigma and tau. And you add one crossing for tau, but none for sigma. And in case 2, now you cross in sigma. So you add one for sigma and one for tau sigma, but none for tau. Oh, this should be sigma tau, I mean. And in case 3, you have 2 crossings, one in tau and one in sigma. But if you think about it, 1 goes to 2 and 2 goes back to 1, you're essentially saying that sigma tau is adding none, because it goes 1 is sent back to 1. So you add none for sigma tau, 1 for sigma and 1 for tau as well. And in case 4, there's no inversions in both, so you add 0 for everyone. And so you can see now, when this is 1 and this is 0, then this is 1. And when this is 1 and this is 1, this is 0. So this means 2 is the same as 0. And when does that happen? In mod 2. So you can really understand why this holds true now when you split it into cases. So it's just like when you count. And the corollary of this is saying that sigma is an even permutation or odd if it can be expressed as a product of even and odd permutation. And this is because if sigma, let's say sigma tau is even, then it must be that it can be expressed as a product of this has to be, this can be even and this is to be even, so that the whole thing works. And hence, every element in Sn can be expressed as either even and odd, but not both. And the reason is because if you have an even permutation times an odd, then what you're left with is an even permutation. But an odd permutation cannot be, but then you now take the even inverse, so it's like odd equals to even times this even inverse, and this even inverse has to still be even, and even times even cannot equals to odd. So there will be a contradiction there when you have both. So every element can only be expressed in either evens or odd permutations, and it really depends on whether the permutation is odd or even in the first place. And so we come with a lemma, and it states that an L cycle is even if and only if the length is odd. And the reason is because a L cycle is expressed as A1 to AL, then this can be broken up into transpositions where A1 is A1 A2 and the next one is A2 A3 and so on. And what you get is that you have L minus 1 terms now of these transpositions. And this is really saying that since transpositions are odd because there's only 2, so they are one inversion only, L minus 1 must be even for L cycle to be even. So this is a product of odd cycles. So in order for this to be even, you need the number of terms to be even. And then we denote the set of even permutations as An. And this An is known as an alternating group, and is actually a subgroup of the set of permutations. And it has order n factorial divided by 2. And it's quite easy to see this alternating group because we know that 1 is the identity is a 1 cycle, so it's an element of An since it's even, so An is non-empty. And if you take 2 even permutations, they can be expressed as an even number of transpositions. And so tau minus 1 and this just means tau minus the inverse of tau can also be expressed as an even transposition. Just take the inverse of every transposition. And this just means that sigma tau inverse is an element of An as well. And so An is a subgroup. As for the order, you just need to apply your combinatorics argument to transform every An into an odd permutation by multiplying a transposition. And you can see that this is bijective. And so An, the even number is the same as the odd, but even plus odd is the total set. So it's just n factorial over 2. So now you have more different types of groups, such as the symmetric alternating groups. And we'll actually see more of these types of groups as we progress. So that's all for this video. I hope you have enjoyed it. Feel free to like, share and subscribe. And I'll catch you in the next one. Bye.